Okay. I am going to give you guys a quick overview of the next chapter here. I know that it's a little bit late. I apologize. I keep getting sidetracked and remembering I'm supposed to do these videos. This is a new way of teaching for me that I need to get better at. But we have let's see, what chapter are we in? I believe we're in the torque chapter, so let's go take a look at this. This is very similar to what we've done before, because we've done forces, we've done circular motion, and this is kind of a combination of the two. So let's take a look here. I'm in definitely the wrong place here, but let's go back a few chapters. Okay, so we did rotational motion, angular momentum already. This is fluid statics. It's not where I want to be. We didn't do angular momentum. Statics and torque, this is where we're at. Okay, so chapter 9, statics and torque, 293. If we go back to our schedule here, let's take a look at when things are due again. Make sure we're up on with this stuff here. So the 6th, which was yesterday, was when linear momentum was due. And hopefully you guys got most of that done. If not, tell me and we'll get you some extensions. But statics and torque due the 8th. I think I'm going to change that really quick because that's tomorrow and I'm just barely getting this thing done. So let's give you guys at least an extra day on that, maybe 2. Let's put that through till maybe let's see here. Let's say Saturday night at the latest, or at the earliest. So we'll move that through to Saturday, and that's open. And then rotational motion is next. Let's see, that's calculus. That's not the one I want to open. Did that one wrong. Rotational motion is this one, which we want to do the 12th, or maybe the 13th. Keep pushing these things out because we're falling a little behind here. So I'm going to change this one to the 13th really quick. Try to get this done. Okay, so anyway, let me go ahead and get back to my textbook here. Chapter 9, torque. Essentially, torque is what happens. Torque is a force that could possibly cause a rotation about a particular point. And so you're going to have a force, and then you're going to have a point that is not where the force is. And you're going to have to create a thing that we call a torque that explains how this thing would feel this rotational kind of force. And we're going to start off by talking about equilibrium again, which is the net force equaling 0, and that means the net force in x has to equal the net force in y has to equal 0. And we've been there before. For static equilibrium, this means that nothing's going anywhere, so it's just stopped. But we also have dynamic equilibrium, which means you're at a constant velocity in a constant direction, and so you can have equilibrium in two situations, motion without motion and with constant motion in a constant direction. As long as you're not accelerating anywhere, you're fine. That's because the sum of the forces is all equal to 0. However, our forces do not always behave like we've been pretending to behave. So here's a hockey stick with two forces on it that are acting opposite each other, and so that they cancel out nicely. However, on the same hockey stick with the same forces in different places now, one higher up, one lower down, it won't cause the hockey stick necessarily to accelerate in a linear direction. It won't push it left or right, but it will cause it to rotate. And this is what we call a torque. So the net force on this hockey stick is still 0 because this force and this force will cancel out, but they will cause a rotation. They won't cause a linear acceleration, but they will cause a rotational acceleration. And so that's what we're talking about when we talk about torque. And you have two forces and you have a distance between them, this distance here. And so that's really what causes the change, the difference there. And so we have to define this torque. Here we have a classic example of torque on a door. You have the hinge down here on the left side, you have the doorknob up here on the right hand side, and if you apply a force out here near the doorknob, you have all of this distance between the hinge and the force that you apply, and it's the same for closing it. However, excuse me. If you want to open the door with the same amount of torque or the same rotational acceleration, and you're closer in, you actually have to apply a bigger force down here. Smaller force out towards the doorknob, bigger force as you get closer to the middle of the door or closer to the hinge. And if you've ever tried to open a door near a hinge, you know that this is absolutely true. It's very difficult to open a door near its hinge. Other things to consider are the angle of this force. This door and this force have a 90-degree angle between them, and that gives you a maximum door opening ability. However, if you push sideways on the door at kind of an angle like this one, you don't get as much maximum door opening power. In other words, it changes the amount of rotational acceleration. If you, of course, go directly in line with the door and just push or pull on it, it doesn't open the door at all. It just pushes or pulls on the hinges. And so there are things to consider. We have to consider the radius or the distance from the rotational point to where the force is being applied, and we call that r, that distance r. We have to consider the angle that the force is making with that r, so the angle between the force and the r vector, the distance vector, we call theta. And it's 90 degrees when you've got this angle like this, and it's 0 degrees when you've got this one right here. And then we define the torque with this letter tau, the Greek letter tau. The torque is equal to the r vector, so that's the magnitude of the r vector times the magnitude of the force vector times the sine of the angle between those two vectors. And that'll give you the magnitude of your torque. Excuse me, sorry. So if we take our hockey stick and we put a nail in the bottom of it here, then we apply this force over here, there is a distance between the nail and the force, which is our r vector, and then there's an angle between our force and the r vector, which is our theta, and the sine theta, when we put the sine theta in there right there, that'll actually change this r into a perpendicular distance r right there. So the perpendicular distance r right here is equal to this r times the sine of this angle theta. And that's where that sine of theta comes in. The units of torque, of course, since they're force times distance, are going to be Newton meters. In English units, it's pound inches or pound feet or whatever. There are lots of different ones, but there is such a thing as equilibrium with torque as well. So here we have two kids on the seesaw, and they are applying forces with their weight downward at different distances. The smaller child is a longer distance away than the bigger child from the rotational point, which is right in the middle. And the fulcrum in the middle here, or this pivot point, is going to apply a force upward that is going to be equal to the forces of the kids downward, as long as this thing's in equilibrium. If this thing isn't going anywhere up or down at its middle point, then there's going to be this force equal to these two forces. However, that does not mean that they won't necessarily rotate, because rotation can still happen, because rotation is not linear motion. So they could rotate, one kid could rotate up, the other one could rotate up or down or whatever else, and we could still have linear equilibrium, but we would not have angular equilibrium. And so if we have complete equilibrium, we would have both angular and linear equilibrium, where it's not moving up or down, and it's not moving side to side, and it's also not rotating in any direction. So how do we decide if this thing, let's see, in this particular example we have the children are balanced, and they tell us that the masses of the children and the distance of the first child are 1, but they don't tell us the distance of the second child. And so we have to calculate the distance of the second child. And for that to happen, the torques have to be equal but opposite. Well, how do we decide if it's opposite? Because torques, how do you decide which direction torques are? Well, a torque is a vector, but it has a strange directional thing. And essentially, as we start off with torques, we're going to say that torques that cause a rotation that is counterclockwise, so going this way around, the counterclockwise rotation will be positive torques, and clockwise rotations will be negative torques. And so if we add the torques together, they should equal 0. So the torque of the first kid is going to be torque 1 equals R1 times weight 1. The sine of theta is going to be equal to 1 because the weight and the R vector are 90 degrees to each other for both these kids. So we have torque 1 equals R1 times W1, weight 1, and that one's going to be positive because it's counterclockwise. The second kid is going to have a torque that's equal to negative R2, W2, because her torque is going to try to cause a clockwise rotation, so it's going to have a negative on it. And then if you have to add those together to be 0, well, then you have the torque of the pivot as well. The torque of the pivot is the distance of the pivot to the pivot, which is 0 times the force of the pivot. Well, since the distance to the pivot is 0, then so you have to do the torque for all three forces, but the third one is 0, of course. And then in the end, you get an equation that says torque 2 is equal to negative torque 1, because torque 1 plus negative torque 2, or torque 1, which is positive, and torque 2, which is negative, have to add together to be 0. Anyway, the point being is that you end up with this equation. R2 times weight 2 equals R1 times weight 1. And then you go ahead and you solve that for R2, which is the distance of the second kid. And then you can get a value for that, 1.3 meters, it turns out. In part B, they ask for the force on the pivot, the force at the pivot. Well, the force at the pivot has to cancel out the two forces from the weights of the children. So you're just adding forces in the y direction. Force of the pivot is up. Two weights of the children are down, so they're negative. You set them equal to 0 because it's not going up or down in a linear fashion. So it ends up you just add the weights together of the kids and you're done. In the second section, they talk about stability, where that has to do with what we call center of gravity, and weight acts on different points in your body because of center of gravity. So you have center of gravities of your arms, the center of gravity of your torso, center of gravity of your legs, center of gravity of your head and everything else, and the overall center of gravity of your body, which is right around your belly button usually. But it can change as your body changes shape, because center of gravity is actually dependent on shape. And the center of gravity can actually be outside of an object, can be outside of your body, depending on what shape you contort yourself into. However, if you're in a gravitational field and you're balanced so that you're not falling, then you're considered to be in equilibrium, but it's not necessarily a stable equilibrium. For example, this balancing child, if she gets just a little bit off, she will fall. So that's what we call an unstable equilibrium. A stable equilibrium is one that if you try to tip it over, it will tip back into equilibrium. It'll go back to its original spot. So we have stable equilibrium and unstable equilibriums. So for example, a pencil, if you try to, a very, very short and very, very wide pencil, a pencil is a bad example. I would say like a 50-gallon drum is in stable equilibrium because you really have to push it way over. It has to be a huge angle for it to tip over usually. If you just give it a little bit of a nudge, it falls right back into place. However, a pencil that is on its tip balanced, which is very difficult to do, could be in equilibrium, but if it tips one way or the other even a little bit, it just falls right over. There's no way for it to tip back. And this is, of course, one of the reasons that athletes get down low. It actually creates a stable equilibrium for them, so that they're not tripping, falling, rolling over or something when they try to do something in their sport. So how do we solve problems with torques? That's what they're talking about in this next part. Well, essentially you're going to have situations where you have forces acting at different points around some center point or some rotational point. And you're going to make three equations. The sum of the forces in the x direction equals 0. The sum of the forces in the y direction equals 0. And then the sum of the torques equals 0. And you may have as many as 3 unknowns now. And you're going to put those three equations together, and you're going to try to solve for your unknowns using those three equations. It's a good idea when you're doing a torque problem that you put your rotational point at a point where there are many forces acting. If you have many forces acting at one point, put your rotational point there. Even if the object is not rotating there, just pretend like it's going to, because you can pick your rotational point anywhere you want for the calculation of torques. But then you have to measure your distances all from that single point during a problem. So let's say, for example, I've got this guy holding the barbell, and we have the center of the barbell here, and I go ahead and say I want my center, my point that I measure my R distances from for my torques to be here. That means you measure your R distance to this force from the right hand, your another R distance force to the left hand, and of course R to the center is going to be 0. And then if I did this problem from that center of that bar where he shifted the bar a little bit, then this distance to the right hand would be shorter, to the left hand would be longer, and so on and so forth. And then, of course, if I did it from here, we'd have these distances out here to these two hands out here. However, if I wanted to choose this point, I could do that as well. However, choosing this point is not a great idea because now I have 3 torques that I'm going to have to calculate. If I choose the point here, then the weight of the bar is right at that rotational point, and that means the torque from the weight of the bar will be 0 because the distance to it is 0. So it's a good idea to choose a rotational point where there are a lot of forces if you have a lot of forces at one point. We have, so this, we're doing one of these bar problems from that previous page here, and you can see that they have, the net torque has to equal 0 right here, and in the end what that really means is the clockwise torques have to equal the negative of the counterclockwise torques. And so you get an equation from that. And then, of course, you get an equation from the y forces, the force of the left and right hands, and from the gravity force on the bar. and then those have to add up to be 0, and from two equations, if you have two unknowns, you can solve for them. And that's essentially very similar to doing force problems, except we've now got a force that can, we've now got forces that can cause rotations because they're acting at different distances or different places on the object. In this section on simple machines, they apply these principles to simple machines like levers, where you have a normal force on the lever here, you have a force that's acting upward here, you have a force that's acting downward from the nail. The nail is trying to push the bar down, you're trying to push the nail up here, and so on and so forth. And so you can, and then you've got, of course, the force from your hand down here. And you can see that the force from your hand is very small because the R is very big. The distance to the rotational point, which I think they're choosing to be where the contact is with the board, is very big there, so a big R times a little force can equal a little r times a big force. And that's the mechanical advantage involved. And here they're using L instead of R, which is perfectly fine. And here they define the mechanical advantage for us engineers here. Mechanical advantage is equal to the force O, which they call the this is the force. What do they? Force O stands for force. I can't remember why they call it force O. But anyway, this is the force at the end where the nail is being pulled. And then this is the force applied by the nail puller. So this is a bigger force over a smaller force, and that's your mechanical advantage. You can also use the distance to the distance to the person pulling divided by the distance to the nail itself from the rotation point. So bigger distance over smaller distance, mechanical advantage is what that's all about. You have the same thing with a wheelbarrow, where your rotation is right here at the wheel. Your center of gravity is pretty close to the wheel, and then your handle is way out here far away from the wheel. So you have a longer distance out to where you apply this small force to lift this big weight here with this big force that's closer. Same thing with a shovel. Right? And here they calculate the mechanical advantage for the wheelbarrow, just using distances. All kinds of machines use this. You have wrenches, you have wheels, wheels and axles and transaxles and everything else, pulleys. You know, they all these machines take advantage of this. And then of course you have these pulley machines where you have multiple pulleys in here. And when you add multiple pulleys, you get even better mechanical advantage because the tension that you apply to a rope out here transmits into the tension here, which of course if you just had the one rope you would just get the one tension, but if you put it through another pulley and tie it back up to this original pulley, then you get another tension here. So you get twice as much tension pulling up this weight. If you do that with another pulley, then you get 3 times as much. And you can even get 4 times as much by pulling in a different direction here. And so just configurations of pulleys can give you all kinds of mechanical advantage. You can do the same thing with gears, and we do the same thing with gears in cars. This next part is actually a lab that we will try to do in our last week, where we have this fake arm, and you're lifting some object here. And the thing that lifts the object is your biceps muscle here, which is very close to your elbow, extremely close to your elbow. And you're lifting up this weight that's not very big, but the force that is applied here has to be huge. So your arm is not a very good machine. It has a very low mechanical advantage because you apply a huge force with your biceps muscle to lift something that's not very big. Well, what's the advantage? Why do we do that? Why is our body designed that way? Our body is designed that way because in order to gain a mechanical advantage, we would have to move this muscle connection way out to our wrist, and we would have webbed arms. And in fact, there are animals that do have webbed arms. Essentially, most jumping animals have tendons that do that in their legs, like deer in their back legs, and rabbits and frogs. They all have this tendon that moves way out here, so they can apply a little bit of force and get a lot of movement in their leg and a lot of jumping power in their legs. So yeah, I mean it does work with some animals, but we are designed to do something else. We're designed to be more flexible and more what's the word for that? Dexterity, to have more dexterity. But anyway, we're designed to have more control and more fine control with our body parts. And so this is how it works. And if you break this down to a very simple model, like a board with forces on it, this is what it would look like. Your biceps muscle would be here. The rotational point is here at your elbow. And there is a force down on the elbow there as well as you pull up here. And then the weight of the book here. So then you also have the weight of the arm at the center of gravity of the arm. So this is your free body diagram for your arm. You have 4 forces acting on it. And if you have your rotational point here, then you're going to have 3 non-zero torques acting on it. And you're going to have to build up an equation. And if you build up the equations here, here's your torque equation. R2 weight A, R3 weight B, and R1 force of the bicep. So this is the weight of the arm, the weight of the book, and then the force on the bicep. And when you solve for the force on the bicep, when you're lifting a book that doesn't weigh very much, it turns out to be a huge number, in the hundreds of pounds, I think. Force on the bicep, 470 newtons, so that's almost 100 pounds of force. And that's just the force that the bicep has to exert. And it's very easy to test that. Pick up a book, put it in your arm, hold the book in your arm at a 90-degree angle, and put your finger on the tendon at your elbow, at the crook of your elbow. And you will feel how tight that tendon is. It's extremely tight. Your back is very much the same way, where you have all these muscles in your back. People who stand up straight don't have to worry about torques in their back, and so their backs don't hurt. People who do not stand up straight get forces that are acting in funny directions in their back, and so they get these torques in their back, which cause stretching of the tendons and straining of the muscles and pain in the back. So good posture is very important, especially when you're carrying things, because when you're carrying things, you're putting more strain on those muscles and tendons. Here they give a problem where you're going to calculate the amount of stress and strain on tendons and muscles in your back here. Turns out to be up in the thousands of newtons, so a couple of 100 pounds of, maybe 300-400 pounds sometimes of strain and stress in your back, and that can cause serious problems. But essentially all they're doing here is they're giving a force and a distance, and you're going to calculate a torque. Let's see if I can see where the distance is in that problem. Right here they say they have this force in the back muscles. They're going to lift a box that's 30 kilograms, and then they tell you the distance. In this case, it's 0.35 meters, so 35 centimeters along the back. And then this one's half a meter here. So different muscles at different distances, and then they're able to calculate that. So yeah, that can be pretty bad news. Anyway, on here they're kind of showing those forces. So here's the force, here's one force, here's another force here, and you can see there's just these tiny little distances, but these huge forces as you lift a box this way. And here's a distance here, 35 centimeters out to here, 50 centimeters out to here. That's a lot of torque that's being cranked around your back. Not a good thing. So that's the idea of torque and statics. It's not really all that different from forces, except that instead of just adding forces together to equal 0, you have to add the forces together to equal 0, plus you have to add the torques together to equal 0. And remember that counterclockwise torques are positive, clockwise torques are negative, and you have to choose a rotational point. So usually the rotational point is obvious in the problem, so it's not a big deal. But you have to choose a rotational point, and sometimes the angles matter. So if there are angles between forces like 29 degrees, you have to take the force times the distance times the sine of the angle. Besides that, it's not all that hard. So go ahead and dive into it and see what happens, see how it works out. Email me if you have a question. I try to answer your questions as much as possible so you can get these things done and we can get ready for our next test, which is coming up in the next week or two. And then after we're done with that next test, well, while we're preparing for the next test, we need to get started on the last couple of chapters and crank those out as well. So we've got one more chapter for the test, because right now we're in chapter 9. We need to go to chapter 10, which is rotational motion and angular momentum. And then chapter 11 is going into the fluid stuff, which we're going to leave alone. And then we need to get all the way to the all the stuff on all the stuff on waves. So that's the thing. Those are the stuff we'll finish up last. We'll do the waves last. And I will, let's see, I made the homework due Saturday. So tomorrow I will try to post a video about going over the homework. You guys try to work on the homework tomorrow morning and afternoonish. And I will try to post a homework thing by the end of the day tomorrow so that I can answer any questions that you have on the homework. And that's all I've got for you tonight. Have a good night.